you got what compound?
It's bromobenzene.
Bromobenzene.
And then it's the 2 lithium reagent.
Yeah, we don't really have a name for that reaction, huh? Just synthesis of an organolithium reagent. And we can call this reagent phenolithium. And there's a byproduct that forms as well, right? Lithium bromide here is a byproduct. And then just one more step.
Yeah. And that's the organocuprate with the CUI.
Yep.
I put 0.5.
Good. Yeah, you put 0.5 in front of it, and that says I need twice as much organolithium per equivalence of copper. But it's a really awkward way to say it. So I think it's best to show 0.5. I wouldn't take off points. I will say you might not see the 0.5 equivalents everywhere. But it's good to recognize. And how did you solve this, Caesar? What was your process? Did you start from the beginning and figure out how to get to the end?
Well, I kind of looked at what I had to go first. So I had to be able to put the lithium in, but I had nothing to put in. So I kind of realized that I needed to put a halogen in. So kind of back and then.
Good. You worked backwards and forwards. You knew that the organocuprate was made from an organolithium. And you knew that to make an organolithium, you'd have to have an organohalide. And then you can convert the organohalide into the organolithium. So that is the process of working forward and backwards. We could have brainstormed along the way before working forward and backwards. We could have just written down things that could work. Like, I know I have an organolithium or an organocuprate starting from just a benzene. So I'm going to have to do EAS of some kind. I'm going to have to substitute a group on that benzene ring. What type of EAS? Depends. But then really that's the best way to do it. One step backwards, one step forwards, meet in the middle. All right, our second synthesis. What's our starting material? Caitlin, do you want to try and give this one a shot?
On like the synthesis?
No, the name of the starting material.
The name of the starting material. It'd just be a 2 butane.
Nailed it. Yep, 2-butane. Your muddiest point last night was nomenclature, right?
Yeah.
Yeah, that's why I wanted to push you there.
Yeah.
Good work. Now I'm interested. Does somebody want to? Yeah.
How many steps minimum to make that?
I'm seeing 4. How about you guys? And did anybody solve this one? You got it in 4?
Yeah, 5.
You have 5 steps. Might be able to do it in 5 steps. We'll see. Do you want to give us your pathway, and then we can maybe look at Sam's pathway too? Who else finished this synthesis? Cool.
I think it's probably wrong, but I have.
Actually, before you get the route, tell me what your process was, similar to Caesar's. Did you work forward and backwards?
Yeah. I try one side, and then once I get stuck, I go the other way, and then I try to meet in the middle.
Sure. So why don't you maybe walk me through how you solved it, rather than just giving me the route. Let's see. What did you do from this side? What did you do from this side?
So I see that we have a alkene. Alkyne.
Yep.
So it's doesn't appear in the end product. So we have to break that up.
Good.
But then I see we have a methyl coming out in both ends.
Okay.
The two.
So
the
4-carbon chain.
one of the bonds have to become a metal somehow. So I started with doing fluoro, two fluoro to break both bonds and have one fluoro substituents.
Cl2.
Yes.
Okay. And you did 2 equivalents of that?
Yeah, so one. Sorry, okay, so I went off the basis that there were two of those with two butanes.
Okay, 2 butynes. Yeah, that's
so
fair.
then I did things separately and then I unite them. With,
Okay. I don't think we'll actually need to do 2 separate routes and have them come back together at the end. The reason being, these 2 R groups that are connected to copper are the same R group. They're both sec-butyl. They're connected to this 4-carbon chain from this secondary carbon to copper, which means we'll just need 2 equivalences of this to react with copper iodide. Does that make sense? Rather than needing to take this butane in 2 separate routes, whatever we do to one equivalence, we'll just use 2 equivalences of it at the copper step. Or in other words, whatever we do to this one equivalence, we'll use half an equivalence of copper to make the cuprate step.
I don't see that.
Not seeing it? All right, let's map out yours then. So if you have it going 2 different ways, is it okay for me to show something like this to show the 2 different reactions you take it on when you bring it back together? I want to see what yours looks like.
Okay.
You had Cl2, and are you expecting this vicinal halide, this vicinal dihalide? Or are you doing 2 equivalences, so you're expecting this tetrachloro product?
Yeah.
It's okay.
So
It's
putting it together.
yeah.
So I think that it's wrong.
Okay.
It's not working.
Maybe you and I can look at it again later, because I'd like to see what reactions you tried to put in there. But this is good. Synthesis doesn't come easy at first. You've got, in fact, when I used to tutor organic chemistry, I would tell students, just do a lot of guess and check. Try a reaction. Does it give you what you want? Go backwards, try it again. And that's hard until you're really familiar with your reactions. Do you guys know how to get really familiar with your reactions? Do you know how to familiarize yourself rather than just memorizing them? How to get familiar with what the reagents are and what they do? Build a big table of them. You put starting materials, functional groups, end products, functional groups, reagents, transformations, and you make all of them. And now you've spent 2 or 3 or 4 hours building a table of all of the reactions, and you'll never forget them. Not to mention you have a resource to go back to study on. Sam, are you willing to share yours?
Sure.
Do you want to give me your thought process, how you worked forward and backwards, if you did?
Yeah. It took me a second to realize that they were the same, like, R group on both sides, but once I did, I knew I just needed to make, like, one of them.
Okay.
I could use. So I first knew I needed, similar to the first one, I needed, like, a BR on for, like, a bromine on, like, one side of the triple bond. So first I just did HBr and then got the bromine on one side, and then it turned into a double bond.
An alkene. Yep, a transformation from.
And so then I wanted to get rid of the double bonds because that's basically our R group.
Yeah.
And so I did H2 or hydrogen. I don't know.
Yeah.
The fancy name is for it. And then,
Hydrogen.
Okay. H2 and then PDC. And so then that just got rid of the double bond.
Hydrogenation.
And then from there, basically just the same steps as the first synthesis, where I did 2 lithium, and then the
Oh, right.
copper iodine half, or single amount
Yeah.
based on.
Yeah, I'll just show you guys what it looks like if you leave off the 0.5. Do you know, almost every time you are running a synthesis, you want to have an excess reagent. And if all you need is half an equivalence of copper iodide, and you add in a full equivalence, then I guess copper iodide is your excess reagent. So maybe that's not such a bad thing to not have half an equivalence. But in the same way that we use 2 lithium to understand the stoichiometry, that's all 0.5 is trying to give us. Anybody solve it differently?
Just slightly different. I just got rid of the bond altogether, the triple bond, and made it an alkane with the H2 and PT, and then added it on with NBS and HV.
Yes. I'm going to put BR2 and H nu. I realized something recently. I had a meeting with an old student who's studying for the MCAT, and they demonstrated that NBS is only used on allylic or benzylic positions, which is not something I had ever seen highlighted in a textbook. But when I scoured Google Images for examples of reactions where NBS is used to do like radical halogenation of an alkane, it's not. So I wouldn't take off points for using it because it's a radical source of bromine, but apparently it is best used on those stabilized allylic and benzylic positions. Same number of steps, but we got there a slightly different way. Both steps involved adding a BR and hydrogenation, but very different. I also wanted to point out, I use palladium a lot, but platinum works just as well for hydrogenation. They're in the same family. They're also in a family with nickel. Nickel is often used as the catalyst for hydrogenation. All 3 of that family, though, very expensive, incredibly expensive metals. I'm not saying you got lucky, but what I will say is that you took advantage of the secondary radical halogenation position, which is where we wanted the lithium to be. So 2 routes, perfectly equal synthesis. Any other ideas of how you could do this? What about just swapping these 2 steps? Having a partial hydrogenation, say H2 with Lindlar's catalyst, or sodium in ammonia, Na in NH3. That would give me partial hydrogenation. Either way would work just fine. It would leave me an alkene. And then I could do HBr or HCl, and that would add 1 chlorine to one of the carbons, 1 bromine to one of the carbons, would work just as well. So, in other words, also swapping HBr for HCl would have worked just as well. Any questions on that synthesis? How does it feel seeing the solutions? For those of you that maybe didn't solve it. Sometimes the feeling is, oh, of course, that's how you would do it. But why didn't I think of that? And if you're feeling that way, it might just be because you just need to familiarize yourself with those reagents. What do I have at my tool belt that I can plug in? What transformation is it going to cause, though? That's the most important thing. I know I have an alkyne, so that limits the reactions I'll do. And what changes can I have it make? Can I bring it down to an alkane? Can I bring it down to an alkene? Can I bring it down to a vinyl halide and then to an alkyl halide? So it also sounds like what tripped you guys up a little bit was recognizing these as the same R group. And it's maybe because I didn't put it as a subscript 2, or was it just because their zigzags are kind of pointing different ways. But when you see copper, I do want you to think cuprate. So you should think two of the same reagent. All right. Before we bring all of this back to alcohols, I want us to take a minute to look at some reactions with organometallics. We're going to look at more of the reactions in these next two sections. But I think we'll save the surprise until then. So these organometallics are strong bases, good nucleophiles, which means that we can have them run nucleophilic substitution. You guys are more used to seeing it written as SN2. We should have a caveat on here. Because these are such strong bases, we really want to prefer primary substitutions, primary alkyl halides. Although you may see it sometimes on secondary carbons. Some people will say that some organometallics cannot be used in certain conditions. Other people will say organometallics can be used in those exact conditions. So let's say that I have something like benzyl bromide. And I want to make this compound allyl benzene. This is not so much a multi-step synthesis that we'd need to do all three of our major steps, like mapping your carbons, brainstorming, and working forwards and backwards. But mapping your carbons is still very useful for predicting what reagent is necessary. So here I can see that I've got carbon 1 on the benzene ring, carbon 2, my benzylic carbon. And in my product, I've got these two new carbons, 3 and 4. Some places that you look will show this bond breaking on the product side. And they'll say, this is the bond that I want to form. 1 and 2 are already present. I need to have a reagent that has carbons 3 and 4. How many different reagents do you think we could use here? Could we use the organolithium? Sure. I mean, it's just got to be connected to carbon 3, the lithium atom. Could we use a Grignard? Sure, it's just got to be connected to position 3. Could we use a cuprate? Yeah, it just needs to be connected to carbon 3. So here are our 3 options. And this one's not really fair because I could say MgBr or MgCl or MgI. All 3 of those would be a Grignard, so they would be equivalent to each other. Writing out the cuprate is the weirdest one because you have to take that bond between carbon 3 to copper and put a parenthesis through it and say 2 equivalences bond to copper. Or you can draw it out, but I think you guys realize drawing out the 2 equivalences looks a little weird. And here I'm just mapping those carbons again so that we can see what's going to happen. I really don't expect that I will be testing you guys on this mechanism, but I have heard from students in the past that seeing the mechanism helps them understand the reaction better. So I'd just like to demonstrate for you guys. Maybe I don't want to demonstrate for you guys. Do you guys want to demonstrate for me what you think the arrow pushing is for this substitution? In my OChem 1 class, I teach electron arrow pushing for the addition reactions first, because those are a little bit more complicated. They've got a lot more going on. And then I come back to teach the SN2 mechanism, and I tell them the SN2 mechanism is incredibly easy. It's just 2 arrows, 1 step. I'm looking at everybody. Come on. Nobody's looking at me though. Or dictate. Tell me what bond to start at. Tell me what atom to point to.
Are the electrons like connecting to the lithium gonna like attack behind the bromine?
Yeah. So the carbon-lithium bond attacks the benzylic position, or carbon 2.
And then
Good. The CBr bond breaks to the bromine. So now lithium is taking the electrons to the benzylic position, correct? No. Lithium does not own the electrons. Lithium is basically a cation there. If you wanted to redraw this, I don't know, somebody might tell you this doesn't exist, that this isn't true. But if you wanted to draw it as that ionic pair, you're not incredibly wrong. It's incredibly close to what that is. So that's our bond formation. I'm gonna abbreviate it a different way now in the product. I'm gonna show you guys that I can abbreviate that benzene ring, since it's mono-substituted, as just pH. And I get a byproduct, LIBr. That's it. Now substitute that for the Grignard. It looks exactly the same. You have an arrow that leaves from the carbon-magnesium bond. And again, I'm not going to have you show this mechanism. To do it for cuprate probably doesn't actually proceed exactly the same way. Copper is a very strange beast. It's not like lithium, it's not like magnesium. Do you know the outer valence shell, or the subshell for lithium and magnesium? They've got electrons in their s orbital, which means that their valence shell is 8 electrons, the s and the p orbitals. Copper is a transition metal, which means its valence shell includes the d orbital as well. So copper has a valence shell that fits 18 electrons. Copper can do a lot of weird things. It can take in a lot of bonds and it can swap bonds around. So the mechanism for copper is probably a little bit different, but you could think of it similarly as well. Okay, so this is one of the great uses of nucleophilic substitution. I want to do another example for you guys. Oh, hang on. So in our product, we're going to have an aromatic ring bonded to an aromatic ring. And we'll have this ortho nitro group as well. And over the reaction arrow, what we'll show is the organometallic of a benzene ring bonded to the organometallic. So whether that's diphenyl cuprate, phenyl lithium, or phenyl Grignard, we'll see all 3 of them doing the same thing here. What would the starting material have to be? Do you see where this shows up in the product?
Would the starting material just be another benzene with the NO2 off of it?
So, nitrobenzene. How would you classify that reaction? It is nucleophilic substitution, but it's no longer SN2. It's now SNAR. You're substituting a carbon on the benzene ring. You're telling me this carbon ortho to the nitro group goes through a substitution reaction. Take off the hydrogen, I put on a bond to a carbon. In this case, another benzene ring. But when we looked at NAS reactions last week, we said they require a specific leaving group. Can't substitute a hydrogen.
So it's that, but with a halogen ortho to it?
Good. So, does it matter what halogen? No. I'm going to put chloro. I feel like we don't give chlorine enough time on this show. So what we see here is a strong nucleophile, like the organolithium and the organomagnesium halide, doing SNAR, NAS, onto the aromatic ring. We have a chlorine leaving group. That's one of the most important things for us. What you might say here is, I'm going to call this carbon 1, or these phenyl groups, I'm going to call that carbon 1, and they're going to attack carbon 2. Carbon 2 then must be on my starting material. That's the bond I want to form. And because carbon 2 is an aromatic carbon, substituting it means SNAR, which means I need to have an aromatic halide, an aryl halide. Good work. Okay, any questions on using these compounds as nucleophiles? What's the main... I'm trying to get you guys to think about what functional groups form, what functional groups leave during these types of reactions. How might you describe the result of nucleophilic substitution with an organohalide? We can't say that it always forms an alkene, because I could have changed this double bond to be a single bond. I could have still run the reaction. I could have made it an aromatic ring. So I can't say that nucleophilic substitution with organometallics forms alkenes or alkynes or aromatic rings or alkanes directly. But what they do every single time is they form carbon-carbon bonds. In fact, I'm not going to put that next to nucleophilic substitution. They do that every single time. That's what organometallics are really good at. They're a negatively charged carbon. They go out and find a partially positive carbon, and they form a bond, and they create a carbon-carbon bond. And I don't know if you guys realize, but it's not that often that we form carbon-carbon bonds. Alkylation and acylation, we formed carbon-carbon bonds there. When we use an alkyne nucleophile, like an acetylide ion, that's an opportunity for us to form a carbon-carbon bond. And then the other 20 reactions we've seen, 20 plus reactions, they all form other functional groups with heteroatoms. Okay, just to give you a preview and not to get into it too much, these reagents can also be used in addition reactions. not alkene addition reactions, but rather conjugate addition and acyl addition. Cuprates here, they deviate from the organomagnesiums and the organolithiums. Cuprates run conjugate addition. So here I have methyl cuprate, and I'm going to react it with a conjugated carbonyl. That means it's a carbonyl that is conjugated with an alkene. You can see that there's an uninterrupted series of p orbitals. An addition reaction is one that consumes a pi bond. And the pi bond that gets consumed in conjugate addition is the alkene pi bond. But it doesn't behave like an alkene addition reaction. It takes advantage of the presence of the conjugated carbonyl. If we're mapping our carbons, we could start at this aldehyde, and we could map the 3 carbons of this structure, and then the 4th carbon that is the methyl group, and we can see that this acyl addition reaction has added a carbon-carbon bond between carbons 3 and 4. It also adds a hydrogen, so there's an aqueous workup here. We're going to dive into these reactions much more in another chapter, one of our last chapters, where we look at these conjugated carbonyls. Organolithiums and Grignard reagents. They run acyl addition. So we're going to look at a very similar thing. We're going to look at methyl lithium. We could just as easily swap this out for methyl Grignard. And we're going to take this 3-carbon conjugated aldehyde. Instead of forming a carbon-carbon bond, between this last carbon in the alkene, I'm actually going to map my carbons the other way. I'm going to map my carbons from the bottom up to the aldehyde. Because the product that I get adds that 4th carbon to the aldehyde carbon. This also requires an aqueous workup. We're going to look at this in the next unit after the midterm. So we'll come back to these reactions. This is really just more of a preview.
There is it. You mean methyl lithium or methyl?
Yep. Not really and, but or. This does actually tell us something. It's not incredibly clear. That is that methyl or organolithiums and Grignards they're actually stronger nucleophiles than, can't say stronger without comparison, than the cuprates. The cuprate is a more moderate nucleophile. It goes to wherever the reaction is stabilized the most, wherever the activation energy is the lowest, whereas the other 2 reagents, they go to where the partial positive is strongest. Some might tell you that organometallics are often used in elimination reactions as well. maybe not often used, but that they can be used in elimination reactions as well. And we're not going to see us using organometallics in elimination reactions, but they can. And there are a couple of other reactions. It kind of falls in between nucleophilic substitution and addition reactions. We'll see these organometallics come back when we use epoxides, and we'll do a ring opening of an epoxide, which is technically substitution, but it's also addition because it consumes a degree of unsaturation. So it's actually a bit of both. But I do want to show you guys one standout reaction of the cuprates. This is unique to cuprates. They can run, they can run vinyl substitution. Vinyl there, not necessarily meaning the 2-carbon chain, but meaning substitutions on an sp2 hybridized carbon, substitutions on an alkene. You guys might remember from OChem 1 that you cannot take something like bromoethene and react it with hydroxide and expect it to do an SN2 reaction. It does not proceed. Reason being orbitals. The direction that the hydroxide needs to attack the anti-bonding orbital does not allow for a low enough energy transition state. It just doesn't proceed. Which makes you think then that you can never do substitution on these alkene carbons until we get to our cuprates. Now I can take something like, well, maybe let's go a little bit bigger and we'll say ethyl cuprate. And we'll react this with this same vinyl bromine. The organolithium, the organometallic, they behave much like the hydroxide. They cannot do this substitution. But the cuprate is not doing substitution in the same way as these other ones. I showed you guys, I'm not going to have you do the mechanism for cuprates, and that's because they actually can take on additional bonds, swap things around, and then push off other groups. They're not doing substitution in the same way. Which means if I see this vinyl halide, I can do substitution with my cuprate. And I can get a compound like this. I also want to ask you guys about the byproducts of this reaction. What do you think forms? Lithium bromide forms. The Br gets kicked off, so LiBr makes sense. What else? What's left over? Copper by itself, just copper plus ion.
The copper in one of the ethyl.
Right. Copper and the remaining R group. I want you guys to recognize that the cuprate reagent is a bit wasteful. You need to have 2 equivalences of this R group, but you only use one of the equivalences. One of the other byproducts is always an R group bonded to your copper. but the cuprates can do reactions that other reagents cannot do. So here it's meaningful to understand why we might want to be wasteful. All right, let's do a couple of practice problems. For the first one? Yep. No. Oh. No. Maybe without this. Maybe if it's just benzene. But try to use an organometallic. I think you lost one carbon. Try mapping your carbons to see where the bond will form. Okay. Not quite.
For the
For the top one. Yep. Oh, not quite. And this one looks good. Yep. Good start. We know it should have benzene. Okay, so I want to pull you guys back together because almost all of you said phenolithium or phenylgrimurid. But I told you not quite. You recognize the change, which was this bond needs to form, so I need to substitute that chlorine directly to a benzene ring. But that's not just any chlorine. It's a vinyl chlorine. That chlorine is attached to an sp2 carbon, which means organolithium, organogrignard, organomagnesium halide, the grignards, they won't work on this position. So what will? Cuprate. And since all I need is to bond to an aromatic ring, then I can have the phenyl cuprate or the diphenyl cuprate. Good. You guys see the application now. You've really just got to identify the difference between a vinyl and non-vinyl. This one actually is allylic, which is different from being not allylic. Allylic kind of has some stabilization from the alkene as well during a reaction, but it's still sp3 hybridized. The most important part in numbering this, or in predicting this product, was numbering your carbons to make sure that you don't lose anything and you don't add anything. So I'm going to give you guys the tip on how I like to number my carbons, especially when it's a nucleophilic substitution. I like to count through the nucleophilic attack. So carbon 1 is on my benzene ring. Carbon 2 is the benzylic Grignard carbon, the benzylic nucleophilic carbon. Carbon 2 will attack the electrophilic carbon 3, and then I've got this carbon chain 4, 5. So when I draw the product, 1, 2, 3, 4, 5, I'll even map them up there again to make sure that I've counted them correctly. 2 bonded to 3, and then 3 to 4 to 5. Could you abbreviate this compound as well? Sure, we could just put pH and then have that carbon chain. All right. Let's take a quick break. Why don't you guys get up and move around and get your blood flowing again so that I can sit you back down and talk to you more.
About one of the
I'll come to you.
problems that
Yeah.
it was from the past one that I cannot get it.
Okay, you know what? This was a more challenging one than I meant for it to be.
Okay.
Do you know this functional group?
I mean, I've seen it before, but I couldn't tell you
Is
a
the
name.
benzene one? Is that?
It's the multi-step.
Yeah.
I'm not coming both with you.
I've been like, I've
Yeah, I
tried
couldn't
a few
figure this one
times.
out either.
So this is an acid anhydride.
Okay.
It's going to behave very similar to the acid chloride. So our first product here will be a benzene ring that's been substituted with one of those carbon groups. So we'll do acylation.
With like,
Just one of those carbons, and then the rest of the chain will come on. Oh wait, maybe reset. No, we don't want this. We'll start with Now, off of any of the positions, let's just go here. You're going to add an acyl group. That's the carbonyl, CO double bond. I think you'll need to add a few more bonds to do it. You're going to draw one of these carbons, and then you're going to have the rest of the carbon chain come around, and you'll have a carboxylic acid at the end. 1, 2, 3, 4 carbons. Good. And this position is the first carbonyl, so that's going to be an acyl group. There you go.
So it broke it.
That's right. It breaks open the anhydride. And then you can see one of the carbonyls keeps the O and becomes carboxylic acid. The other carbonyl lost the O, took on a positive charge, acted as the electrophile. I forgot that I had this one in here. Ralph brought it up the other day. It's not meant to be more challenging, but meant to show you that you can use a lot of other functional groups. Not just the acid chloride, you can use the acid anhydride. There's another reaction where you can use an alkene that forms a carbocation instead of an alkyl chloride. What does this reaction do? Gets rid of carbonyls, but actually it gets rid of aldehydes and ketones. It won't reduce the carboxylic acid. Yep. I wish there was a way to copy and paste. Good. That's it. Now, SOCl2 is not a reagent that I teach in my OChem 1 class with the carboxylic acid. It's actually one that we'll see in a few weeks. But it is used in OChem 1 with alcohols. It takes the OH, substitutes it for Cl. And it does the same thing here. So that's going to turn your acyl, that'll change your acyl group from a carboxylic acid to an acid chloride. Now that you have an acid chloride and AlCl3, that's going to run acylation. And you have an alkyl group already attached, which means the alkyl group will direct the acyl group or the active side. The alkyl group directs the acyl group or the. That's chlorination. We're going to do acylation. So we're going to add an acyl group to the benzene ring. That acyl group. It's going to loop around.
Oh, yeah, I was never going to get this.
I never gave you guys intramolecular reactions with our benzene reactions.
I haven't done those for a while, yeah. I remember doing them slightly in OChem 1, but we didn't even do it on 10.
That's it. So you've made a bi-cyclic structure in the process. You're welcome.
I was like, I tried a few times. Google never helps with like this kind of stuff. Not like.
Well, actually, I have something to say about that. In my years as a tutor, I did a lot of Zoom tutoring. We were always online, so when they would come up with a question that I had not seen before, or that I wasn't exactly confident in answering, I could usually find the question on Google before I even needed to give an explanation. They'd show me something, I would recognize I didn't know it. Using the internet to find the answers to challenging questions, though, requires that you can phrase it correctly. So you've got to be able to identify the functional group. If you can't identify the functional group, that's where you have to start. Two carbonyls connected by an oxygen. Oh, an anhydride. Okay, an anhydride with AlCl3 in a benzene reaction. There you'll probably find at least one resource that has shown it. And then you can, and then you can say, for some of my students a couple of semesters ago, they said, I don't know if the carboxylic acid and the ketone will both be reduced with the zinc mercury step. So we Googled it. Zinc mercury with carboxylic acid, nothing comes up. Zinc mercury with ketone, lots of reactions. So shows us that you can't reduce a carboxylic acid with it. That gives us a better idea of what's going to happen. So it is a learning curve, but it's asking the right questions. You know, this analysis assignment that I give you guys, pick a molecule and we'll just analyze it all semester. I've had a similar type of assignment I've wanted to do, which is pose you guys a question that you can't possibly answer with your knowledge, that you'd have to go and ask the internet for resources on, but it's hard to ask, it's hard to word, and then come back at the end of the semester and give you that same question and see just how much terminology you've learned, how well you've been able to frame your thinking so that you can actually tackle that question. Like my OChem 1 class, I would maybe give them an organic molecule and say, what's the product formed? And they wouldn't even know what to search up because they don't even know what functional group is there. And then bring it back to them towards the end of the semester and they can say, what functional group does 1-butene form when it reacts with acid? Because it's a learning process and you do have to hone in on that skill. All right, guys, let's transition from organometallics back into alcohols. We're going to start with preparation of alcohols. Preparation, now that I'm saying it, feels kind of like a big word. In the context of OChem, you might just think of this as synthesis of alcohols. How can we prepare alcohols? And I always like to start with reactions that we have seen. So, previously. This might be a good time for you guys to maybe flip back in your notes and compare how many different ways have we already seen alcohols formed. So why don't you guys break up into one big group or a few small groups, look through your notes together or brainstorm. How many different ways do you remember forming alcohols? Just take 5 minutes, flip through as quick as you can and see what comes up, and then we'll look through it together.
This is just from our notes from all of this class.
I mean, we have reviewed them during the first couple of weeks. We reviewed a lot of our reactions. And if you don't see them in those notes, then you might just think about them. Rob, Caesar,
RCO.
how many did you guys find?
Two.
I mean, this one's pretty quick, how much so fast.
Addition.
That would have carbon.
That was the
That's
same
not
as
all.
substitution.
And
Okay.
this one.
Oh, so you found there
is
are
the-
addition reactions
the oxide
and there are
reaction.
substitution
What
reactions.
exactly?
You want to do
Reaction.
the rest?
I want you guys to be thinking about specific reactions
Oh, so they,
because I'm going to show specific reactions.
so they make the reaction one.
There's halo hydrogen.
That's all that I have.
How many did you guys find?
What is this one?
Quite a few.
Quite a few.
Yeah, I'll let me keep count.
No, it's okay. Really, it's fine.
And now I want to now. Two, three, four,
And also.
five, I have six.
Good. I have 6 too.
This is on our other times.
Now imagine if you had a nice table you could just pull up and search by alcohol, and you just have
Like
all
on
of them.
Excel?
I don't know.
Huh?
Like on Excel?
That's how I made my table. I made it on Excel, and then I could organize my functional group product, and I could. Yeah.
For me, it doesn't help me memorize it. It'd be like a nice reference, but like memorizing it, this
I have to write them.
helps me remember it better than practicing synthesis. Actually helps me like get it in there.
I do think that writing it out. Studies have shown that writing it out will lock it in your head better. But any time spent with it is better than no time spent with it.
Yeah.
And why not give us an Excel sheet?
Why would I do it?
Why not?
Because I'd be robbing you of the learning experience.
These
Can
copies.
you show us how to format it?
The way that I made it was actually not that good. It was very ugly. I was a junior in college, and I also was not very good with Excel. I'm still not. But all of my classmates asked me for it, and none of them ever complained. I don't know if any of them ever improved it. They never gave it back to me. It wasn't the best. I have seen a lot better tables from students of mine over the years than the one that I actually made. That's why I won't do it. All right, so we're going to start with our substitution reactions. So we saw SN1 and SN2 substitutions with water and hydroxide. I'll give maybe one example of SN1, one example of SN2. Does that sound good? So here I've got 2-bromo, 3-methyl butane reacting with water. That's a secondary position, a weak nucleophile. So a carbocation will form. That carbocation will rearrange to the more substituted position. And the alcohol that I get is 2-methyl 2-butanol. Now the same thing, same starting material, but instead I'll use hydroxide, and now my reaction runs through SN2. I'm going to specify low temp so that I promote substitution and I don't promote elimination. Because it's SN2, no carbocation rearrangement. If I had stereochemistry shown, I would have seen inversion from wedge to dash, from dash to wedge. Correct me if I'm wrong, that's all of the substitution reactions that are useful for forming an alcohol. Take an alkyl halide, swap it with water or hydroxide. Then we're going to move into addition reactions. We'll look first at acid-catalyzed hydration. This is one of the most common and useful ways to do addition to an alcohol. I want to take this opportunity to remind you guys that the reaction arrow doesn't really matter. The reaction arrow is just a place for us to collect reagents that are going to be used. I think you'll often see H2O on top, H3O plus on bottom. It's very common to place a solvent on the bottom and catalyst on the bottom and an active reagent on the top, but it truly doesn't matter. This reaction has a carbocation intermediate. So it's going to form the most stable carbocation, which would be on the secondary position. And that secondary carbocation will rearrange to the tertiary carbon. So the product that I get here is, once again, 2-methyl 2-butanol. If we're thinking about byproducts, our first reaction, SN1, has a byproduct of HBr. Our second reaction, SN2, has a byproduct of Br minus. Is there a byproduct in this acid-catalyzed hydration reaction? Nope. You can see that there's an equivalence of H that's added across the alkene and OH. And by definition, H3O plus is there as the catalyst, so it's not being consumed. So there's no byproduct. Water is added across. To give us a comparison of acid-catalyzed hydration, we're going to look at oxymercuration, reduction. Some of you may have learned this reaction name as oxymercuration, demercuration. But I really do want to emphasize the fact that it is a reduction step that follows, because we'll be looking at reduction reactions in just a second. We'll take the same starting material because it helps us identify why it's useful to have a different hydration reaction. Over the reaction arrow, I'm putting first mercury acetate followed by sodium borohydride. The first and second are incredibly important. If you don't explicitly say first mercury acetate with water and second sodium borohydride, then you are explicitly stating to mix everything together in the same pot. And you will not get the desired product if you mix everything together. This reaction is also Markovnikov, but it avoids rearrangements. It has no carbocation intermediate. So now I get something that adds alcohol, Markovnikov, without the risk of a rearrangement. And the third type of hydration reaction is the hydroboration oxidation. It is funny to me that some people call this the oxymercuration demercuration, but they don't call this reaction hydroboration deboration, because you do remove that boron group at some point.
Doesn't sound as good.
I hear you. It doesn't sound as good. We're going to start again with the same 3-methyl 1-butene. First, we'll add borane. And just a reminder that a lot of places will show you also THF. THF is just an inert ether solvent. I'm not sure why people are so hung up on using THF with it and not diethyl ether. There might be a reason that is not explicitly stated in places. Followed by basic aqueous basic aqueous hydrogen peroxide. H2O2, H2O, and AOH. All the H's, all the O's. And this is an anti-Markovnikov addition reaction, which means that instead of getting 2-methyl-2-butanol, instead of getting 3-methyl-2-butanol, I get 3-methyl-1-butanol. 3 different structural isomers from the same starting material. That's the usefulness of having 3 different hydration reactions. Another one is the syn-diol addition. There are 2 reagents that give us the same product. We can use OSO4, or we can use cold potassium permanganate, KMNO4. And I do want to add here that these are often added with acid. Sometimes you'll see something like this. That's a carboxylic acid with a little tert-butyl group. Oh, I don't know why I put a C there. That's weird. CH3, 3C, COOH. On my material, it's less likely that you'll see the acid added. The acid is needed, otherwise there's no hydrogens with these reagents. Now this is syn addition, so these groups are on the same face. They're either both wedged or both dashed. We'll be spending less time with stereochemistry this semester, so it's less of a priority to highlight that. So far, I'm hitting all of them. The last one that I have is the halohydrin addition. For this reaction, I want to demonstrate an unsymmetric alkene. An alkene that has 1 carbon more substituted, 1 carbon less substituted. There are 2 halogens that are commonly used here. We could use Br2, we could use Cl2, but it's important that with either one, we run the reaction with water. This is an anti-addition mechanism, or an anti-addition reaction. But again, the stereochemistry, a little bit less of our focus here. When we get back to epoxides, we'll look more at the stereochemistry there. Notice the regiochemistry of the product. The alcohol has added to the more substituted carbon. The halogen has added to the less substituted carbon. When you dive into the mechanism, you start to understand that the halonium ring, when the halogen bonds to both carbons of the alkene, is stretched more from the more substituted carbon, putting more of a partial positive on that carbon, making it easier for the nucleophile to attack there and break that bond. Did I miss any from what you reviewed?
I have the anti-dehydroxylation.
Oh, anti-diol addition.
Yeah, that's how I have it written from my last semester. Is that one? And then I kind of added what we did, where we didn't open up the ring; we just left it when we learned it.
Yes. Okay, so the way to do anti-diol addition is to first form an epoxide.
Yeah.
And then follow up that epoxide with acid. And we're going to look at that in the epoxide section.
Mm-hmm.
So we'll come back to that. There is, we're not going to come back to that. We're going to look at it next because this is all previously, and I don't think that I showed it to you guys.
No, you just showed us
Previously.
the making of the ring. You didn't open it, but
So we're going to look at that next. We're
Yeah.
going to say there are new ways to form alcohols. This is not all of them. Are there any from the review that you guys did that I didn't put up here? Good. So moving from our previously seen reactions to now. Let's start with this epoxide ring opening, because I think that's a really useful one for us to see. The other way to call this is the anti-diol addition. Or maybe we should call it what you had, anti-dihydroxylation. Reason being, if you already have an epoxide, you might not necessarily call it an addition reaction. Although I mentioned earlier, opening an epoxide is both a nucleophilic substitution and an addition reaction because you add molecules. You decrease degrees of unsaturation. You increase saturation. So the easiest way to look at this is just to start with an epoxide and show what reagents we can use. If we have H2O and H3O+, then we form a diol. Excuse me. If we looked at the stereochemistry more, we would see that the epoxide sits on one face, and after the addition reaction, the two alcohols sit on opposite faces. We can run this exact same reaction with different reagents. We can actually run this with hydroxide. Sorry, I'm going to clarify. We can run it with hydroxide, then follow it with acid. If I ran the reaction with just basic conditions, I would end up with a basic product. If I want to have a protonated product, I would need to follow that reaction. And then this can be coupled with epoxidation. So if we start with an alkene, then we can say first I'll run MCPBA. Remember that MCPBA is a peroxy acid. It can be generalized as CO3H. That forms the epoxide. Then acidic conditions, H2O, H3O+, H2O, H+. I do want you guys to feel familiar with abbreviating acids in different ways this semester. H plus is one of the most generic ways to abbreviate an acid. It doesn't tell you if that acid is aqueous or if that acid is organic. Later on in the semester, we'll use H plus in some reactions, but it's really hard to use H plus in a mechanism. It's easy to forget what you're looking at. This could be H3O plus, it could be acetic acid, it could really be anything in this case. Again, if we were looking at the stereochemistry, and if you are interested in adding the stereochemistry in here, these OH groups will be opposite of one another. One will be wedged, one will be dashed, which is a direct contrast to our syn-diol addition, where both alcohols would be wedged, or both alcohols would be dashed. And the process here involves this intermediate. I want to show us the peroxide intermediate or the epoxide intermediate that forms. MCPBA does epoxidation. Following that with acidic water opens that into our diol. Does anybody need a picture of the board before I erase it? Are you guys good? Okay. The next way that we can prepare alcohols is through reduction of carbonyls. Now this is going to be a big section, so I'm going to actually preface this with some reducing agents and compare them to the carbonyls that they are useful for. We're going to look at the acid halide, the aldehyde, the ketone, the carboxylic acid, and the ester, just for now. Acid halide, aldehyde, ketone, carboxylic acid, ester. These are actually arranged from order of strongest partial positive on the left-hand side to smallest partial positive at the carbonyl carbon. Why does the carbonyl carbon have a partial positive? Bonded to an electronegative atom. I think you guys would agree there's a resonance form of all of those carbonyls where oxygen is taking the electrons and putting a positive charge on the carbon. One of the reducing agents that we'll use this semester is called sodium borohydride. NaBH4. Sodium borohydride is a moderate reducing agent. It can do reduction, but not incredibly well. Well, actually, I don't think that's giving it enough credit. it can't reduce everything. If the carbonyl is not electrophilic enough, sodium borohydride will not work. So we can see that sodium borohydride will reduce acid halides, aldehydes, and ketones, but it will not reduce a carboxylic acid. It will not reduce an ester. Then we have a stronger reducing agent. This is known as lithium aluminum hydride. Although I typically will refer to it as LAH, and its chemical formula LiAlH4. This strong reducing agent can reduce any of our carbonyl groups. This is an aggressive reagent. I do want to take a second to point out what is inside that name. That name says hydride. IDE tells us something negatively charged. Hydride tells us we're looking at a negatively charged hydrogen. We are essentially looking at H- with this reagent. Without it being H-, because we know we can create H-, we can provide sodium hydride, NaH. That is H-. Hydrogen is more electronegative than boron. Hydrogen is more electronegative than aluminum. So when hydrogen is bonded to boron and aluminum, it is taking the electrons for itself. Aluminum and boron are in the same family. They prefer to have 3 bonds to complete their octet. When they have 4, they have an excess amount of electrons. They take on a negative charge. But who owns that negative charge? Who is using that excess in electrons? Hydrogen. So these two reagents are essentially a source of H-. If you think about where H- is going to go in these reactions, it's going to be drawn to the region with the partial positive. It's going to be drawn to our carbonyl carbons. So we're going to form a bond to H in these groups. I don't really have enough time to get us to dive into these. So I think instead we'll pick up here tomorrow. Here's the framework that I'm going to lay it out with. Well, maybe I'll ask you guys if you have an opinion. We can either take each of these functional groups and look at the alcohol they form by reduction, or we can look for different types of functional groups. Methanol, how do you form methanol by the reduction of one of these? Primary alcohols, which of these will form a primary alcohol? Secondary alcohols, which of these will form a secondary alcohol? Tertiary alcohols, which of these? Those are our 2 ways to do it. We can either look at each functional group and what it forms, or we can focus on what type of alcohol will form and which of the functional groups will get us there. So think about that, how you'd like to see it tomorrow. Would you like to see it from the perspective of each of these going to form an alcohol, or would you like to see the big families of alcohols and which of these functional groups can help form them? Meditate on that. I'll see you guys tomorrow morning.